Hey everyone, it's Mr. Canfield, BC Calculus. We are starting chapter 20 today, also known as comparison of series. So, to begin, we look at a couple of series that we've seen before, and then we run into some problems with them. And the problems are things like, wait, this doesn't completely match things that we've seen before. So like, I can use Nth Term Test on both of these, and I can show by the Nth Term Test this diverges, but by the Nth Term Test, this could converge. The problem is this doesn't really fit into any of the molds that we have to figure out what to do after. So it, with analysis that we've seen before, you can kind of figure out what to do and find out the convergence or divergence, but it's always been kind of a fuzzy math. It hasn't been a legit math way to do it. So today we're going to delve into legit math ways to handle it. Additionally, like you got things like this, 1 over n squared versus 1 over n squared plus n. This we can use p series. This is not technically p series, and so we're like, well, what do we do with that? This one, 1 over 4 to the n, that's a good old geometric. This is no longer geometric. It's got that stupid plus 1. So what happens here? And if you think you have an idea for what happens with these three, that's awesome. A lot of people develop an intuition about these sorts of things that is pretty reliable. We can use the integral test on this. This is not integrable. And just in case I've never told you that, e to the x squared and e to the negative x squared, these are not integrable functions, meaning we cannot take the integral of them and get a function, which is pretty wild. And just take my word for it. Don't dive deep into it. I had a student do that a couple of years ago, and they went a little crazy trying to figure out why those don't work. It's a thing. Don't worry about it. All right, anyway, so there are two comparison tests that allow us to compare an unknown series with complicated terms to series with simpler terms. So what we're going to do basically is we're going to take a series and we're going to compare it to 1 over n, 1 over root n, 1 over n squared, or a geometric. There's a way to compare them and prove through that comparison convergence or divergence. So, so one of them is called direct comparison. So if 0 is less than, this is meaning if we're dealing with just positive terms. And notice how A is smaller than B. So if we know that B converges, if B's big, look at this. A is smaller than B, that's what that means, right? Doesn't matter what term you're at. If each term of A is smaller than each term of B, well then if B converges, then we know that A converges. If B diverges, we don't know anything about A though. Like, right, if we're looking at this on a size chart, so size here, and then we have A and we have B, and like A is here and B is here. If I tell you that B converges, well, B is bigger than A, so of course, if something bigger than this converges, then that has to converge too. Let's flip that around though. If I tell you that this diverges, we don't know if this is guaranteed to diverge, because this is smaller than it. So this could also diverge, but it might not. What we could say though is, if I know that the smaller one diverges, well then the bigger one diverges too. So, like if I can maybe represent these with a curve. Here's, let's start with B. Here's the curve of B, and we'll just like, here's where it's converging to. B is converging to this. If I tell you A has to be smaller than it, what does A have to do? A can do like whatever the heck it wants, but at some point it's going to have to like squeeze in here and converge as well. Now let's reverse this. Let's say that B diverges. Well, we know A is smaller than it, so A can do whatever it wants. It could go up here and diverge as well, or it could just come down here and converge. So there's, if the bigger one diverges and the smaller one, it doesn't tell us anything. But what if we take the smaller one and we say, hey, the smaller one diverges? Well, what's the bigger one? Bigger one's like, I don't want to diverge. Oh, I have to, I'm bigger than you. So, It's kind of an ambidextrous thing here. A and B kind of are swappable. But let's look at this. 1 over 3 plus 2 to the n. Well, let's compare this to just regular 1 over 2 to the n. So we can call, I don't want to use A and B. Let's call this series M and series E. I don't know. So if we look at series M and we plug in 1, we get 1 over 3 plus 2, which is 1 over 5. And then we get, I'm just looking at the terms. I'm not caring so much about the sum of them right now. We get 1 over 5, then, so what is this? You know what, I should do E first. E is gonna be easier because I'm not dealing with the plus 3, and then calculating M will be easy. So 1 over E, if we plug in 1, oh, it starts at n equals 0 on this. So let me start with n equals 0. So that's 1 over 1, then 1 over 2, then 1 over 2 squared is 4, then 2 to the third is 8, 16, etc., right? Those are the terms of E. So if I look at M, when I plug in 0, that's 1, so it's 4. It's 4, 5, and so I'm just adding 3 to each of these. 1 over 7, 1 over 11, 1 over 19. So look at how all these compare. Which is bigger, M or E? At each term, E is bigger than M. And we have a question now. What do we know about E? So there's a hint. It says n equals 0. That's a big hint there. The other hint is that it's not n to a power. If it was n squared, this would be like a p series. But this is the other way around. This is a geometric series. And so because of that, I want to kind of think about this as 1/2 to the n. And if we remember how geometric series works, right? I always read it as earn, and that's kind of how I remember the writing of it. If the absolute value of r is less than 1, then we're good, it converges. So r is 1/2, it converges. This is a convergent series. Since this is convergent, but E's bigger than M converges too. M's smaller, so this thing's convergent and this is smaller than it, so this is convergent too. I pretend I wrote converges by direct comparison to 1 over 2 to the n. That's how this works. So if you can find a buddy that does something and you know exactly what the buddy does, then you know what this thing does. All right. So let's look at our next one. Number 2 over 1 over 4 plus root n. So this to me looks like 1 over root n. Let me, I'll call this one y and I'll call this one o. All right, yo. All right, so for y, we're starting at 1, right? So if I plug in 1, I get 1 over 1. Plug in 2, I get 1 over root 2, 1 over root 3, 1 over root 4, 1 over root 5. If I look at O, I get 1 over 5 plus 1 over 4 plus root 2 plus 1 over 4 plus root 3. Oh, this is 1/2, isn't it? It doesn't really matter, right? So if I'm comparing these two, look at, so y was the first one, right? So 1 over 1 compared to 1 over 5, that's bigger. 1 over root 2, 1 over 4 plus root 2, that's bigger. Bigger, bigger, bigger. So series y is bigger than series O. So if I can show that series y converges, then series O converges. So series y, oh wait, series y is 1 over n to a power. This is 1 over n to the 1/2. And if you remember p series, p of 1/2 actually means this diverges. So this is bigger, it diverges. What does that tell me about O? Nothing. Unfortunately, this was kind of a waste of time. This direct comparison shows us that series O doesn't necessarily diverge. It's smaller than it. So y diverges, but O might not. So let me try, and the thing is on the AP exam, they'll usually tell us what direct comparisons to do. So if they told us use a direct comparison to 1 over root n, what does it tell us? The answer would be nothing. It tells us nothing. It tells us no definites. But I'll change to series n. I'm going to make a new one. And series n, they're telling me to try 1 over n next, right? So series n, so y was a waste of time. Let's look at n. 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. Key thing to note here is, as I'm comparing these, 1 over 1 is bigger than 1 over 5. So, right? Yeah. Wait. My brain's breaking. Hold on. Okay. Yep. 1 over 1 is bigger than 1 over 5. 1 over 2 is bigger than that. Shoot. 1 over 3 is bigger than that. Shoot. 1 over 4 is bigger than that. Shoot. 1 over 5 is bigger than that. Shoot. Wait. Why are they telling me to do this? These are all bigger. Let's skip to like 1 over 100. Oh wait, I don't even need to skip to 1 over 100. Looks like we need to skip to, let's just like skip to 1 over 8. Compare 1 over 8 to this. Right, because it's 1 over 4 plus root n. So if we look at the bottom here, if you don't know, square root of 8 is, it's less than 3, right? Because square root of 9 is 3. So this is somewhere between 2 and 3. So 2 point something. What's 4 plus 2 point something? That's like 6-ish. Okay, so 1 over 6 versus 1 over 8. This is now smaller. So we've reached some place where n became smaller than O. And let's continue out toward infinity. You know, let's go out and say 4 plus the square root of 100 and 1 over 100. Well, this one is going to be 1 brain. Brain, where are you? Oh yeah, it's 10. So this is 1 over 14. 1 over 13 versus 1 over 100, which one's bigger there? Because this was our series O and this is our series N. Well, 1 over 14 is bigger than 1 over 100. So O eventually becomes bigger and it stays bigger forever. What do we know about series N? What do we know about the series 1 over N? There should be a name that comes to mind with this series. I've mentioned it every class this comes up. This is called the Harmonic Series. And Harmonic Series is famous for diverging. This diverges, but it's smaller than O. O is bigger than this harmonic series, than N. That means that O has to diverge too. Since N diverges off to infinity, and O is bigger than it, I mean, O starts out smaller than it. It's like down here, smaller than it, and then it gets bigger. O has to diverge too because it's bigger. So that's how we do direct comparison. We just test turn by turn, term by term is what I meant to say. And we're gonna get to a point where one is always bigger than the other if it's a good enough, if the comparison that we've been asked to do is good. One is bigger than the other, and that'll tell us either convergence or divergence through comparing them to each other. So I can definitely help you with this personally, but I think this is, it's really worthwhile to kind of struggle through it on your own instead of just like watching countless examples. It's more like, okay, I'm here, what happens? And you just kind of have to analyze it. Okay, so we also have limit comparison test. This is different. So if you have two positive series, what you do is you take the limit of the two series divided. If the limit exists as a positive finite number, then both series do the same thing. They either both converge or they both diverge. And the idea here is that as we're getting out to an infinite amount, if you look at these two series compared to each other, are they the same level of extreme? If one's way more extreme than the other, way more infinite than the other, then this limit's not going to exist, or the limit's going to be zero. It's either going to blow up to infinity or shrink all the way down to zero. And in that case, it's kind of like they're different power levels of infinity. We're trying to find two things that are the same power level at infinity. So let's do an example and then see if that doesn't help. So, all right. So if I look at 1 over 3 plus 2 to the n, well, I'm going to compare that to 1 over 2 to the n. So what do we know about 2 to the n? We know that 2 to the n converges. So I'm going to take the limit as n goes to infinity of this. And you might be like, whoa, 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 that is, no thank you. Well, look, dividing by fractions is super easy, right? This literally means 1 over 3 plus 2 to the n divided by 1 over 2 to the n, which is the same thing as saying 1 over 3 plus 2 to the n times 2 to the n over 1, which is the same thing as saying multiply the tops, 2 to the n over 3 plus 2 to the n. Okay. So what's the limit? Oh, by the way, this flipping thing happens so frequently. You're going to jump from here to here 99% of the time. So what's the limit as n goes to infinity of 2 to the n over 3 plus 2 to the n? So, okay. The long answer to this is plug in infinity. Oh, I get infinity over infinity. Oh, infinity over infinity. I have to do L'Hopital's rule. That's the long answer. So do L'Hopital's rule. You know the derivative of 2 to the n is 2 to the n ln 2. If you don't know that, study harder for your AP exam. The derivative of 3 is 0, then 2 to the n ln 2. Wait. The limit as n goes to infinity for this is 1. That means that as we approach infinity, these two series are of the same strength and of the same nature. So, well, what does 2 to the n do? Or 1 over 2 to the n, we said, is convergent. And if you're not sure why, we did it earlier in the video, pay more attention. But this is 1 over 2 to the n is the same thing as saying 1 over 2 to the n. Why did you write 2 there, buddy? N. Because if you distribute the n, you get 1 to the n over 2 to the n. And our ratio is less than 1, so this is a convergent geometric series. So, hooray, convergent. So since this converges also. All right. Immediate question is probably, well, what about one that like is divergent? Yeah, maybe we'll do that next. All right, next one. We're given 1 over 4 plus root n, and we'll compare that to 1 over root n. Take the limit as n goes to infinity. And remember, 1 over root n is a divergent series. It's a divergent p series. So we'll do the flipperoos. We'll get root n over 4 plus root n. And here's the thing. Yes, you can use L'Hopital's rule for this. You get infinity over infinity. No, you don't need to do L'Hopital's rule for this if you know, oh, the derivative is at 0, the derivatives are going to cancel. It's going to be 1 again. If you need help doing L'Hopital's rule on this because you cannot see the lines where this goes, I'll help you out. You just got to talk to me. I'm not gonna spend video time doing that. And there's other ways to think about it too and get 1. But we get 1. We get a number. Cool. That means, great. They both do the same thing, and we know that that diverges. Therefore, that diverges. The way that I would personally look at this is I'd go, that's 1 over root n. That is also 1 over root n. At infinity, the 4 is irrelevant, so they're the same. It starts to get messed up when it's like, if that had been a 4n plus root n, then that's kind of all bets are off, and I'm not as sure at that point. Most bets are off at that point, and I'm not as sure. So I'm just going to go through and double check some answers and make sure I didn't miss anything so far. Yeah, okay, we're looking good so far. Okay, let's look at number 5 now. So this is the divergent harmonic series. Show that trying to prove this using direct comparison test with 1 over n is inconclusive, but using the limit, no. I'm trying to streamline and rush through my curriculum at the end of the course. So maybe one day I'll go through and do that, but for now, these videos also serve as a lesson planning tool for me, so I'm skipping that. All right, so for the following series, use the limit comparison test to determine if it converges or diverges. Okay, so the first one we have here is 1 over 3n cubed minus 5n plus 7. And we have to decide what we're going to compare what we're going to compare this to. I know what I want to use. So let me just kind of walk through what we're going to do for these 4 problems. What we're going to do, we're going to compare it to another sum, and we're going to see, like, does it work? Are we good? And go from there. What I'd recommend, though, is before we even start, take a guess. I would imagine many of you know what this does. So I have a guess. I have a secret guess. I will, actually, I'm going to write down all 4 of my secret guesses right now. You write down your secret guesses, too. Okay, I've got my secret guesses for all 4 of these. All right, so I'm going to compare 1 over this to 1 over n cubed. That's what I'm going to use. I know that 1 over n cubed converges, so, and I think this one converges as well. I'll do the flippies. This one is very easy to do L'Hopital's rule. If you can't see it, that this goes to a third. But if you can't see it, you can get 3n squared over 9n squared minus 5. Not integral. Still get infinity over infinity, so we'll have to do it again. 6n over 18n minus 5 is gone. N's cancel, we get 1/3. So this has a number for our limit of 1/3, meaning they both behave the same way. So since that's convergent, the other one, the one that we're looking at, is convergent. So 6 is convergent. All right, let's look at 7. All right, and I'm gonna use a wrong one in number 7. So number 7, I'm gonna compare this to 1 over n squared. This is not a good comparison to do. Square root does not look like n squared. If I were to compare these, I'll do the flippies. I'll get n squared over the square root of 4n minus 2. I get infinity over infinity, so I guess I'll have to take so I'll do L'Hopital's rule. So that was 1 over the square root with a 2 out. It's 1/2 times 1 over the square root and then multiply the derivative of the inside. Can cancel that. I can flip this up. Oh, cancel the 2's. So I can flip this up and I say n times the square root of 4n minus 2. When I plug in infinity here, I get this is going off to infinity. This test is inconclusive. I'm supposed to get a number. If I don't get a number, the test is inconclusive, and I picked a bad comparison. So the comparison that I should pick is 1 over square root of n. So when I do this divided by that, it flips up here. I get square root of n over square root of 4n minus 2. We'll take the limit as n goes to infinity. And just checking my time. Very cool. So here, as we go out to infinity, we get infinity over infinity, which is 1 over 2 root n. This is 1 over 2 root 4n minus 2. Then there's a 4, that pops out. Those cancel, we have a 2. So when we flip this around, we get 4n minus 2 over 4 root n. Okay, square root of 4n minus 2 over 4 root n. Oh, excuse me. And it looks like this is headed off to 1/2 here. So, which actually, let's go back here. This is n to the 1/2 power, and this is 4n to the 1/2 power, right? That's the minus 2 doesn't really get affected. So this is n to the 1/2 over 2n to the 1/2 as we're going out to infinity. This is really just a half. So that little shorthand and cheating is, please do that. So since this works, then we know that this and 1 over root n do the same thing. 1 over root n is divergent. This is divergent. All right, let's look at 8. So I'm actually, okay. I might surprise you. If you think about this at the infinite scale, baby, 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 n squareds are babies, and the n cubed is a baby, is the only one that's not a baby at infinity. But if I look at n squared versus n cubed, they kind of look like 1 over n, if nothing else was here. So I'm actually going to compare this to 1 over n. And hey, it might not work, but that's what I'm choosing to compare this to. Actually, maybe you were thinking that you were going to compare this to 1 over n cubed. So let's try 1 over n cubed really quick. Let's see what happens if we compare those. Well, then this chills, and this gets flipped like that, right? So the numerator is going to turn into n to the 5th minus 5n cubed. The denominator is n cubed minus n squared minus n plus 2. And so as we go out to infinity, we just need to focus on the biggest exponents. We see we've got a bigger exponent on top. This tells us this is flying off to infinity. This is divergent. So unfortunately, this doesn't give us any information, and this was a waste of time. But what about 1 over n? That reasoning I was bringing up earlier. So let's try that. So n squared minus 5, we're going to multiply that by n instead of n cubed. So that's going to give us n cubed minus 5n over n cubed. See where I'm going now? N squared minus n plus 2. As we go out to infinity, this is just going to 1, right? We only care about the biggest term. It's going to 1. So they behave the same. Hey, what does 1 over n do? 1 over n diverges. So does this. Final question, number 9. 30-minute lesson. Number 9. So this one is not as easy for me. All right. What am I going to pick for my comparison? This is hard. I'm gonna cheat. What's he using for his comparison? Stu, that work isn't very helpful. Okay, I'm just going to tell you that we are going to use 2 to the n over n squared for our comparison. Wait, why do I even need to do that? Hold on. Do the nth term test on number 9. I feel like Stu's missing something giving us number 9. If I just do nth term test, do you see it? I don't know if you can see it. We get infinity over infinity, so I'll take the derivative, and I'll get 2 to the n plus n 2 to the n ln 2 over 12n squared. It's still infinity over infinity. I'll take the second derivative. I get 2 to the n ln 2. Hopefully you see, we are having continual stuff on the top, and the bottom is eventually going to shrink to 0. We're going to do L'Hopital's rule a few times. The bottom is going to turn to 0. And so this is going to turn into, or it's going to be eventually just be a number, right? It's going to be a bunch of stuff all going off to infinity over like 24. So this whole thing is going to infinity. The nth term of this goes to infinity. Nth term test fails. I don't need to do limit comparison. I'm done. This is divergent. The nth term test tells me this is divergent. I shouldn't use other tests if the nth term test tells me it's divergent. I'm done. Okay, so that's that. And then if we move on to the homework, it's just 12 questions where we are using comparison. So this is definitely an AP topic. It's a thing that shows up. I know I poo-pooed the integral test. This test is very helpful. It's very much a thing. So yeah, bye.